Hi everyone, it's Miss Coyle here. Just wanted to talk to you all about one of the questions from the 2014 physics exam that involves oscillation and mass oscillating on a spring. Now it seems the last few exams we've had several oscillation questions, and I just thought it'd be worthwhile going through this question with you all, just to really highlight some of the things that you want to watch out for. So the scenario is that we have a 40 centimetre spring. When it's loaded with a mass, it's obviously extended, so we have an extension that is going from the point where it's 40 centimetres. And we've been given a table here that highlights the length that we see when we have it extended. So the first part of the experiment that's described in the question is adding consecutive masses and seeing an extension, and we're asked to find the spring constant. So to do that, we're going to use the force equals kx relationship, and we need to remind ourselves that there is a negative there, but when we're actually working for the spring constant, we don't need to use the negative, but remembering that the negative is representing the fact that the force that is being within the spring is in opposition to the direction that the spring is stretched, and that's why it's a negative. So then we need to just think about the values that we've got. So we're asked to find a spring constant, so we're going to have to decide on a number of masses and then an extension. So I picked the two masses, which is 100 grams, remembering we need to change it to 0.1 of a kilogram. And then the extension is at 60, or the length is at 60 centimetres, so it's going to be 60 take away 40, so a 20 centimetre extension. So got to remember that they're giving us a spring length, and we have to take into account that the relationship is about the extension of the spring, so how much it's stretched. And then substituting that in for K, that's pretty straightforward to prove 5 newtons per metre is going to be the spring constant. I would hope that everybody would get their 2 marks for that question. Okay, the second question, what happens now is that we're told that they now attach 4 50-gram masses and release it from its unstretched position. Now, what's going to happen now is if they lift the mass up to the point at the very beginning and then they let it drop freely, it's going to oscillate. So what that means is, if we have a look at the picture, what that means is if they hold it up here and then they release it, it's going to bounce up and down about a midpoint. And we have to identify what distance is it's going to be at its final stretch, so when it's going to get down to here. Now, to do this, we're going to be thinking about the energies that are involved in this scenario. So if it's stretched to a certain point when it's just hanging steady, if we then pull it back up to its original position, so the position from here to here, it's going to have a certain amount of potential energy that when it's at its lowest position down here will be converted into the energy that's stretched in the spring. So potential energy up here will be equivalent to the energy in the spring when the spring is completely stretched, and then it's at rest when it reaches the bottom of its oscillation, which means that we're going to be looking at mgh at the top at the release, and that's going to be equivalent to a half kx squared at the bottom. So that's what we need to be thinking about when we actually look at the problem for the second question, because the second question asks us to find the extension that the spring has when it's oscillating at that momentary position at the bottom of the oscillation. So again, first things we need to do is we've got 4 50-gram masses, so we need to recognise we've got 0.2 of a kilogram, and then I've just written here we need to consider this energy. So at the top before release we're looking at mgh, at the bottom when it's at rest, it's the total energy is going to be held within the spring at half kx squared. Now remember, that distance h, the change in the distance that's happening, is actually that value x that we're looking for, because if you recall, what we're actually being asked is to find the distance from here to here. So if the potential energy is here, is going to be against where it's at the bottom, so we're after that distance from there to there. So I'm just making x equal to h, and then I'm going to substitute in the values that we know. So g times the mass times h, which is x, is going to be equal to a half times k times x squared. And so then we're just going to solve for x. So 2 times that. Remember, we're going to have an x on one side and x on the other side, so that'll divide through. So we cancel one of the x off. and that gives us a size of 0.8 meters. So what this tells us now is that this would extend to 0.8 meters before it comes to rest. Okay, now the next part of the question continues this idea of examining the energy that's going on. So Joe and Sam measure the four masses as they oscillate up and down, and they've plotted a graph of the two energies that are involved. Gravitational potential. So here's our gravitational potential. At the top it's at a maximum, at the bottom it's at its minimum, if we call that bottom our 0 point, which we did in the last question. And then the spring potential energy, at the top is 0 because it's not stretched, and then by the bottom it's stretched to its maximum, which is the same height as the potential energy, and so it's got its maximum potential energy there. So Joe says that the calculation must be wrong because the graph should add up to a constant amount, the total energy of the system. However, Sam says that the graphs are correct. And then we are asked to explain why Joe is incorrect. So we've got 2 marks, and we've got to think about 2 things that we can say distinctly. Now, they give us a particular direction in this question, which we need to make sure that you follow. So your explanation should include the reason that the spring potential energy and the gravitational potential energy do not add to a constant amount at each point. So we've been given a very clear direction, so we need to make sure that we actually follow that direction. So we're going to consider the graph and think about a point on that graph, and that's what I've labelled here. So I've gone and labelled a position on the graph here, and I'm calling that A. I can choose anywhere on the graph, so I've picked a position that I can see clearly goes through some of the grid lines, which will make my counting easier. The other thing I've done is I've noted that there are actually 9 grid lines. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can quote the total energy. If the energy budget is kept constant, then it means everything should add up to a flat line across the top. That should be our total energy of the system, and that should be constant, as we know from the conservation of energy. So I've said consider the point on the graph A. The 2 graph energies of energy of the spring and energy of gravity only add up to 7/9 of the total energy. So how did I work that out? Well, from here to here is 1, and then 1, 2, 3, 4, 5, 6. So if I add this bit to there, I only get to here. I don't get to the top. So I'm only adding up to 7/9 of the total energy of what it should be. So I'm answering this question by considering the addition or that it doesn't add to the constant amount we're expecting it to. I then have to explain what's going on, and hopefully what you realise is, remember that this is an oscillation, which means there's movement, and what hasn't been considered in these 2 energies is the fact that there's kinetic energy as well. So my second statement says the graph does not take into account kinetic energy of the moving mass. So there are my 2 points. I've answered the question by identifying that it doesn't add up the way it should, and I've identified why, because they're not taking kinetic energy into account. Okay, the last question in this problem is worth 4 marks. So it's a considerable part of the problem, and it requires several different steps to get to the answer. So our last part of the problem is to calculate the maximum speed of the masses during the oscillation and to show our working. So the first thing we need to think about is, where is the maximum speed going to occur? And remember, this question hopefully has led you into this question to get you thinking about kinetic energy, because we're going to use the fact that there's a difference in the energy budget to determine where that is going to occur. Now, our first step, as I said, is to work out where that maximum speed is going to occur. So if we go back to our actual oscillation picture here, remember that we release it here, it starts to fall. It'll be falling under gravity, but remember, because of the spring, there will also be a force pulling up this way. So what's actually going on here is there's going to be the force of the spring pulling up in this direction, and there's going to be the force due to gravity pulling down in this direction. Now that's going to happen as we fall, and as the string gets further and further stretched, this force is going to get larger. This, of course, force due to gravity is a constant, so it's going to stay the same. So there's going to be a point where these two are going to be equal to each other, and that point is going to be where it's travelling at its fastest. So if you imagine as this mass is falling down and the spring is stretching more and more, this force of the spring trying to pull it back up is going to overcome this force of gravity trying to pull it down for an instant, and we're going to end up with an F net, so the net force, equaling 0, and that will happen midway through, and that's going to be where it's travelling at its fastest. Then as it goes further along, it's going to eat into FG. It's going to keep pulling it down until the force is so large that it's going to now bring it to rest. So at this point here, it's travelling at its fastest speed. Any point after here, this force is going to be larger than the gravity force, which means it's going to slow our object down until it comes to a rest. And then that force of the spring is going to start dragging it back up again. So where after this instant here, where F net equals 0, and we can use symmetry to suggest that it's going to be midway through the oscillation. And so if this is 8 centimetres from here to here, then we would imagine it's 4 centimetres from here to here. However, we can also prove that using our analysis of F net. So if we go back to our problem, we first off tell the examiner that we recognise the maximum speed is going to occur midway when the force of the spring cancels due to the force of gravity. That is, our net force is going to be equal to 0. So that means the force of the spring will equal the force of gravity at that particular point. I then am going to do some analysis. The force of the spring is going to be equal to kx. The force of gravity is going to be equal to mg. So I can then do some analysis on that and rearrange to find that indeed it does happen at 0.4 of a metre, which is the midpoint as we suggested. So now we know this piece of information, we can use that to look at the energy that's going on in the system. We know from over here, we know that the total energy of the system should be equal to the gravitational potential plus the spring potential plus the kinetic energy. Now remember, at the top and the bottom, it's not moving. So at the top and the bottom, the total energy budget is only made up of either the potential energy at the top or the spring energy at the bottom. So there's only going to be kinetic energy when it's in motion between these 2 points. What this means is we can use the situation at the top to determine what the total energy budget of the system actually is. So using mg energy that's going to happen at this instant. So we know that the total energy in the system is 1.6, and we're using that at the top of its flight using mgh, and that we got from question B. So at 4.4 we have to substitute it in to this set of equations. So our 1.6 is our total energy, 0.2 times 10 times 0.4 is our m times g times h, and then the energy of the spring is a half times 5 times 0.4 squared, that's our half kx squared, and then the unknown is a half times 0.2 times v squared, and then we're going to rearrange all of that to solve for v, which is a little bit messy. This calculates out to 0.8, this calculates out to 0.4, that times 2 is this half that's been brought up to this side, and then the square root of the whole ended up being 2 metres per second.